Number 62. White vinegar is 5.0% by mass solution of acetic acid in water. If the density of the white vinegar is 1.007 grams per centimeter cubed, what is the pH? Okie dokie. So, a lot of review here, but then we're going on to new stuff, right? There's a couple of things that they didn't tell you that we need to know in this problem. Now, the first thing is, what is acetic acid, right? Acetic acid comes from acetate, the polyatomic that we know and love. And if it's an acid, you just tack on a hydrogen. So I just wrote down what acetic acid is down here. So this would be CH3, C, O2H. Now, acetic acid is not one of our 6 strong acids, right? There's only 6 of them that you guys should memorize. So all other acids would be classified as a weak acid. All right, so we're dealing with a weak acid here. Now, they do tell us that we have this acetic acid in water, and that it's a 5% mass solution. So that's review. I don't know what chapter that was, right? That was way in the beginning when we learned a mass percent formula. The mass percent formula is this one right here. So we're going to be doing a lot of review for this one probably, guys, right? Percent mass is always the grams of solute divided by your grams of solution times 100. Now, the only thing that they told us was that the percent by mass was 5%. So I'm just going to scribble this out, and I'm going to say, okay, we know the percentage, right? 5%. But they didn't tell me how many grams of the solute that I have, or they didn't tell me the grams of solution. Let's figure out which one is which here. Now, they did tell us that we had the acetic acid in water, right? So, in this case, the solute is the acid that's going in the whole solution, which is the acetic acid in water, right? So, basically, I can just erase the solute, and I'm going to say that my solute is the acetic acid, CH3, C, O2H. Now, the solution is the whole entire thing. It's the acetic acid plus the water, right? If I just had to write up here, the acetic acid is the solute. The solvent is the water, so H2O. That's the solvent. And together, once you place the acetic acid in the water, that becomes now the solution. But they didn't give me any numbers, right? They didn't tell me how many grams of acetic acid I have, how many grams of the solution it was, right? Now, the total thing that they're saying here is if it's acetic acid in water, they're calling this vinegar, right? White vinegar is acetic acid in water. So maybe if I just got rid of this, right, solution, we could just say that this is the white vinegar. I'll just put vinegar just for short here. Now, let's just try to find out this ratio. Now, when they don't give you any values for the grams, now keep in mind, we can't use this density over here because this is grams per centimeter cubed. We're only looking for grams of the acetic acid and the grams of the vinegar. But we can use this formula to help us, right? If we want something to stay 5, right, and it's being times 100, if I want to get rid of this 100, I would basically divide by 100, and the 100 cancels out. So I can use that in terms of this. This grams vinegar is in the denominator. So if I just move this over, and I say that I have 100 grams of vinegar, the 100s cancel out. And now you're only left with 5. So 5 equals how many grams? Yeah, 5. So because by doing this little trick, we actually can figure out how many grams of the acetic acid I have and how many grams of the vinegar, right? So now I'm just going to write that down. We basically have 5 grams of the acetic acid and 100 grams of the vinegar. And then we don't need this formula anymore, but we used it to get us actual numbers. Okay. Now, let's see. We're asking for the pH, and we have a weak acid, right? Anytime that we're using weak acids or weak bases, we think of a balanced equation, but we have to use the ice table. We don't use ice tables for strong acids or strong bases, but I know that I'm setting this up for an ice table. And if we're doing an ice table, do you know the only unit that's allowed? Molarity. So we have to use a molarity, and maybe I'll put that over here. We have to use a molarity. Now, before I even do that, I just want to say that, once again, this is the solute, and this is the solution. Okay. Now, just knowing the grams isn't enough. I need to find out the molarity, right? And the molarity, remember that formula all the way back in the day, right? It was always moles of the solute divided by the liters of the solution. Now, the solute is the acetic acid, and the solution is the vinegar. But we don't have the right units. Basically, we have to take these grams. I have to take the 5 grams of the acetic acid and somehow turn this into moles of acetic acid. And now the numerator is satisfied. And what do I have to do with the solution? I got to turn the solution from grams into liters. And then from there, I can divide the two numbers and I will have a molarity. So, first let's work on that. Maybe I'll just get rid of this because this is a little sloppy. But this is basically what we're doing now. Okay, now 5 grams of acetic acid to moles, that's all the way back in the day, right? Converting from grams to moles. We just use a mole ratio. So let's do that. 5 grams of CH3CO2H times by that ratio. We know how to go from here, right, guys? Grams of CH3, CO2H on the bottom, moles of CH3, CO2H on the top. And remember, this is periodic table. 1 mole equals whatever the mass is on the periodic table. That goes in the grams. So let's get out our periodic tables. Got mine right here. Got my calci, and let's just figure out how many grams is in 1 mole. All right, so let's see. Carbon. I'll try to get the exact number that I see on my periodic table because I don't really like to round. 12.01 plus 3 times 1.008. Then we got another carbon, 12.01, plus I got 2 oxygens. Each one is 16, plus 1 more hydrogen. So that's 60.052. Okay, grams cancel out with grams. And now we found the first part. 5 divided by 60.052. We're still not at the exact answer that we want for the pH, so try not to round. I'll extend this a couple of decimals. So 0.08326. And that is now moles of the CH3CO2H. So we found out what this number is. We found out that it's now 0.03626 moles of the acetic acid. Okay, first part check. So maybe I'll put a check here. And since we have a lot of work here to do, I'm going to erase this. So we're going to be erasing throughout the whole video here. So pause the video if you need to write this conversion down, but we got to move on. So bye-bye. Now we got to convert 100 grams of the vinegar into liters. Okay, now keep in mind, grams is a mass and liters is a volume. Do we remember that formula that we can go from a mass to a volume? This is also way back in Chem 1. The density formula, D equals M over V. Now, if we have the mass and we're trying to solve for the volume, we need to know the density. And it has to be the density of the solution, aka vinegar. But there we go. If the density of white vinegar is 1.007 grams per centimeters cubed. So we know this density value. Now, we can basically use this formula to solve, right? Or we could just rearrange this formula just to get volume by itself. And what would happen is the volume would come up here, boop, and the density goes on the bottom. So it just makes it easier for the video. But you could have used D equals M over V to get that as well. Okay, now here's a little hard part, right? They told us that the density was 1.007 grams per centimeter cubed. And the mass we just said was 100 grams, right? And since the unit grams is the same, grams and grams, we're going to plug this in. I don't really like to change these density units if I don't have to. I like to change them afterwards. So what we're going to do is we're just going to solve for the volume. And we can do that because the masses will cancel out. So in this case, we have a volume of something over something, 100. And when I like to do the math, I don't like to put in any numbers because I just check beforehand. So it'd be 100 divided by 1.007. So let's see, 100 divided by 1.007. Once again, this is not the answer, so I'm going to try to give myself a few decimals. So 99.3049. And this has to be in the unit of the density. The density was in centimeters cubed. That's the unit for the volume. So at this stage of the game, this is 99.3049 centimeters cubed. But remember, we want that volume in liters. Now, also another thing to remember is since we're dealing with the solvent water, right? Density of water is 1. So 1 mil would equal 1 centimeter cubed. Okay? So hold on, maybe I can just move this over. So it doesn't matter whether you say centimeters cubed or you say milliliters, they are exactly the same. So 1 for 1. So if you have 99.3049 centimeters cubed, you really have 99.3049 milliliters. And now I can get closer to those liters. We can use our dimensional analysis to go from mils to liters, right? If I just times by ratio, I throw the milliliters on the bottom, liters up top. 1 liter always equals 1,000 mils. This is from all the way back in chemistry land, number 1. Gen Chem 1. So I'm just going to take that number, 99.3049, divided by 1,000. Just move the decimal to the left 3 times, 1, 2, 3, if you want to do that as well. And this would equal 0.0993049. And now that's in liters. So we found out the volume. So what I'm going to do is I'm just going to take this number, plug it in here. Here's the liters. Okay. So pause the video because we have to do more math. I'm just going to get rid of all this density conversions. So bye-bye. Okay, now remember, we need to get molarity. Molarity, just like we said before, molarity equals something over something, right? It's the moles of the solute divided by the liters of solution. So that's why we had to do all this hard work, because the moles of the solute is what we found up top here, 0.08326. And the liters is the 0.0993049. Let's figure that out. And now that will be the molarity of our acetic acid. Because whenever you're finding a molarity, you're finding it for the solute. So in this case, it would be molarity of the acetic acid. So 0.08326 divided by 0.0993049. And now, this is still not the full answer. So we'll give it a few decimals. 0.838, I guess we'll give it 4. 0.8384, and that's molarity of the CH3CO2H. Okay. And I guess I'll do that in blue. All right. So all of this math that we just did was to basically start the problem, right? Because we still want to find the pH. pH comes from the dissociation of our weak acid. And in order to find a pH, if we want to look a little further now, we need to find that concentration of just H+, aka hydronium. So what I'm going to do is I'm going to pause the video. And, well, I'm not going to pause the video. If you want to pause the video, we're just going to get rid of this molarity concentration. So that goes bye-bye. Whee! And I'm going to put this up here because this is important. And now what I'm going to do is I'm going to make my balanced equation with my acetic acid because that's the acid that ionizes, right? So the trick with acids, which is great, is that you could always write the acid down, CH3CO2H. And since this is a weak acid, it will be at equilibrium, so I do need to see those double arrows. But with acids, it's pretty easy to write the balanced equation because you just strip away the acid, the hydronium ion. So basically, you split it into an H and the rest of the compound. So in this case, I'm just going to say, okay, this was CH3, CO2, the acid lost its hydrogen, and that becomes a minus, plus the H that was given up, and that's the H at the end of the compound, and that's H+. So with acids, you don't have to write it in water, but with bases, you have to get the balanced equation. Okay, so now as far as states, weak acids and weak bases are going to be aqueous, they're in water, and then any charged species that has a charge at the top, that's also aqueous. So all three of these are going in our Ka expression. And we also had to pull the Ka from the back of a textbook because we can't answer this question without it. The Ka is 1.8 times 10 to the negative fifth. All right, so actually what I'm going to do is I'm going to pull this over here because we're going to start our ice table. So let's split it. Split it. Let me make this a little bit nicer. Let's bring this down. This is all over the place. I wrote this on a slant. That's okay. And then we'll do I, C, E. That's my ice table. Okay. And maybe if I can just pull this up a little bit, that's fine. All right, so I stands for initial. It's the initial molarity that we found of the acetic acid. And that's why we had to do all that work to find out that molarity. So my initial molarity is 0.8384. They did not say that I started off with any acetate ion or hydronium, so I have to assume that both of those are 0 and 0. C stands for change. It's the drop in concentration from what you started with and the increase in concentration of your ions. Remember, you can only go up from nothing, right? You can't go any lower than what you don't have. So if you see zeros, you know that the change in concentration is always going to be positive on this side, which means that on the reactant side it will be negative. But I don't know the change, so I'm going to label it as X. Right, so minus X, plus X, and plus X. And with acids and bases, the ratio is always going to be a 1 to 1 to 1, so you don't have to worry about like plus 2X or plus 3X. It's always going to be XXX. Now, E stands for equilibrium. It's the initial with the change. So 0.8384 minus X is literally just 0.8384 minus X. 0 plus X is just X. 0 plus X is just X. Okay. Now we have our equilibrium line, and we're going to use this equilibrium values with the Ka expression. Remember, Ka is always equals to products divided by reactants, right? And you can only use aqueous or gases, but in this case they're all aqueous, so we're going to use them. So if I just write out my fancy little formula here, Ka would equal products divided by reactants. So it's the two products, they're being multiplied by each other, divided by the one reactant. So we have acetate, CH3, CO2 minus times H plus, and then CH3 CO2H. Okay, so we have the values. Let's just plug them in. Ka is what we had to get in the back of the textbook, 1.8 times 10 to the negative fifth, equals. So we have the two equilibrium values on the top, x times x. And then we have the one equilibrium value on the bottom. But now here's the thing. If we include this minus x value, the math is going to get crazy. And we don't want to do hard math here. We don't want to get out the quadratic equation and do all that. So there's a trick here. What I like to use is if you see that you have a Ka that's very, very, very small. In this case, it's a number times 10 to the negative fifth. That's a really small Ka. That means that at equilibrium, you are going to be mostly reactants. So if you start with all reactant, you didn't have any products. If you started with all reactants and you're going to end with mostly reactants, did this X change? No. I mean, the change is going to be so small that it's probably not even going to change this number too much. You're probably going to still be very, very close to 0.8384. So in terms of simplicity of doing the math, we can kind of say this minus x is so small that I can negate it. And I can only put the 0.8384 at the bottom here. Just going to make life much easier when we try to do the math. Now, let's do the math, right? We're going to cross multiply here. So this times this. And x times x is x squared, right? So we have x squared equals 1.8 times 10 to the negative fifth times 0.8384. And I get 1.50912 times 10 to the negative fifth. I want to just get x, so I have to take the square root, right? The square root of a square is the opposite. And now I'm just going to find out what x is. Oh boy, what did I do? Oh boy. Hold on. Okay, there we go. So square root of the answer. And we're getting closer. So I'm going to give 0.00388, we'll say, right? And this is x. This is going back to the equilibrium line, so this is a molarity. Okay, so maybe if I can, I will get rid of this and the molarity up top here. Actually, I think I can do it from here. I just want to get rid of this formula, right? So hang tight, guys. Actually, I think if I just move this over a little bit, I have some room over here. And that's what I will do. Okay. Now keep in mind that we solved for x, right? And we want to solve for the pH. Remember, the pH is the negative log of the H plus concentration. So we just solved for x, and look at what x was. X was the H plus. So we know that this is 0.00388 molarity, which is going to go, boop, right in here for the H plus. So pH equals negative log of 0.00388. And we're going to find our answer. Oh my goodness. So negative log of 0.00388. And we'll get 2.41. And that is our final answer. And thank goodness it's acidic, right? We're dealing with an acid here. So if you got like a pH of above 7, go back. You could always check yourself here. So we should have a acidic number. So if you got like a 9 or a 10, go back in your math. Something went wrong. But I really, really hope this helped. Let me know in the comments. This one was a crazy one, a lot of review, but it's kind of good. We got to bring those things to the forefront sometimes. I hope you guys are having a great day, and I will talk to you in later lessons. Okay, bye-bye.